Okay, hello everyone to today's seminar on interval methods in control engineering. And it's my great pleasure to introduce today Brenner Rego from the University of Minas Gerais in Brazil, where he's currently a postdoctoral research fellow. And at the same university, he also received his PhD degree. I think it was in 2021. And before that, he spent almost 1 year in Italy at the University of Pavia. And his research interests focus on fault diagnosis, modeling and control of unmanned aerial vehicles, and is especially also on dealing with aspects of bounded error state estimation, and that's also the area where his presentation will come from today. He will talk about set-based estimation of nonlinear discrete time systems using constrained zonotopes. Brenner, we're looking forward to your presentation.
Thank you, Professor Andreas. Today I will present one of the topics that were addressed in my PhD thesis. It is set-based state estimation of linear discrete time systems using constrained zonotopes. This presentation is divided in 4 parts. The first one is an introduction to set-based state estimation and constrained zonotopes. Then I will talk about the methods for state estimation of systems with nonlinear dynamics. Then in the third part, state estimation of systems with nonlinear measurement and invariants. And then lastly, I'll talk with a brief overview of the work and future directives. So I will start the presentation with this figure, which illustrates one of the most used methodologies for set-based state estimation for nonlinear discrete time systems. Given a set containing the previous states and bounds of the process uncertainties and measurement uncertainties and the measurement itself. First, we have a prediction step, which is similar to reachability analysis. And it computes all the set containing all the possible trajectories of the system given this previous set and the bounded process uncertainties. Then using the measurement and not explicitly the inverse, but the result is like an inverse mapping of this function. We compute a set of states that are consistent with the measurement and the bounded measurement uncertainties. Then lastly, we have the update step, which is the intersection of these 2 sets. So zonotopes were first used for state estimation of nonlinear systems in the work of Kahn. I hope I'm spelling correctly. I don't know exactly how to spell this surname. And zonotope is basically an affine transformation of a unitary box in which you have 2 variables, which is the center and the generator matrix. And this set become popular in state estimation with the fact that the linear mapping and coefficient can be computed very efficiently and only occurs a very slight increase of complexity of the zonotope. However, there is an issue. The intersection that is required in the update step is not a zonotope, and it's usually addressed through conservative intersection with scripts. Constrained zonotopes were introduced in Scott et al. In 2016. It is an extension of zonotopes in which besides the center generator will have also equality constraints. And it results in being, instead of an affine transformation of a unitary box, you have a constrained box, and the affine transformation of this constrained box gives the constrained zonotope. So for constrained zonotopes, we have also the linear mapping and coefficient are easy to compute. But in addition, we have the capability of computing the generalized intersection between 2 constrained zonotopes, which is a constrained zonotope, and it's as easy to compute as the 2 previous operations. Just an example of how easy is linear state estimation with constrained zonotopes, given this linear system, dynamic equations, the measurement, and the bounds on the uncertainties. The prediction step is given by this equation, which is only composed of linear map and coefficient. This is the same of zonotopes. Because in the update step, you have a very simple expression, which is composed also in coefficient and linear mapping, but we use the generalized intersection to do the intersection between the predicted set and the set that is in the measurement space. Just a quick word on complexity reduction, because this operate as in case of zonotopes, the operations with constrained zonotopes increase the number of generators and constraints. So we are here, constrained zonotopes also have to use methods to enclose the set by another one with lower complexity. In the case of zonotopes, we just need to reduce the number of generators, and there are several methods in the literature for doing that. And they, depending on the method, they have relatively low computational cost. In the case of constrained zonotopes, it's a bit different. We have to reduce the number of generators, but this requires to move the set to a higher dimensional set, which increases a bit the complexity. And besides reducing the number of generators, we need to eliminate constraints to reduce the number of constraints. And these additional steps give a relatively high cost in comparison to zonotopes. But it's still very, let's say, it's relative, it's just a comparison between zonotopes and constrained zonotopes. Now I move to the second topic, which is state estimation of systems in nonlinear dynamics. So we will first deal with this kind of system, which a discrete-time system with nonlinear dynamics and linear measurement. The uncertainties are bounded by convex polytope sets, including we assume that we know initial set containing the initial state. The problem is solved using a prediction of the algorithm as well as in the classical case. But in here we have that the prediction step is nonlinear. These methods that will be presented in this part, they were published in this paper in Automatic, which was a collaboration with Professor Joseph Scott from Georgia Tech and Professor W. Raymond from the University of Pavia. So the first proposal is based on the mean value theorem, which is basically we try to manage to extend the method that was proposed in et al. In 2005, that is zonotope method to constrained zonotopes. The idea is using the mean value theorem, if f is continuously differentiable, so just to set a constrained zonotope, choosing an approximation point inside the state set, you have that besides given an interval matrix that contains the Jacobian of the function, you have that this equality holds for any point inside the state set and the disturbance set. But okay, how do we use this equality? This equality has a direct implication, which this the function, I mean I can say the next state, it will belong to this, it's guaranteed to belong to the set in the right side. However, here you have a product between an interval matrix and a constraint zonotope. We do not have yet no way to calculate this before this work. So we propose a new operator, which is called this inclusion. And this is also a generalization of a method that was proposed in Lam et al. It was called zonotope inclusion. Basically, is an operator that computes a constrained zonotope that contains the product of the interval matrix and the constraint, say the product between an interval matrix and a constraint zonotope. And this can be used in the result that we got is the mean value theorem. This method requires to know a zonotope that contains the constraint zonotope Z. And the proposal is to compute the zonotope by eliminating all the constraints from the constraint zonotope using the constraint elimination method proposed in Scott et al. So with this, we can develop the method for prediction step based on the mean value extension. and basically the result that was obtained before. But here we assume that we know a zonotope, a constraint zonotope that contains this set. And here we replace the product between interval matrix and the constraint zonotope by the cis inclusion. And finally, we have a valued enclosure for the prediction step, which is a constraint zonotope. Since this set is a constraint zonotope, the update step, which is linear, can be performed easily by this equation here, which is the same from the linear case. The second proposal is based on the first order expansion, and this is an extension of the method proposed in Bastell 2005, that was as Rego zonotopes, which was extended to constraint zonotopes. In this case, I will skip a part of the derivation of the result because it's quite involved and it's present in the paper. But basically, you can have a second method to compute a bound of the enclosure for the prediction step. It's given by this expression here. To a remainder term that is a constraint zonotope, given by this octet expression here. Since this enclosure is a constraint zonotope, the update step can be, which is linear, can be computed easily by this expression through the generalized intersection. So besides, since the two proposed methods, we rely on the choosing an approximation point, either for the mean value theorem or the first order Taylor expansion. And for each one, we propose a different heuristic. In the first case, to take into account the zonotope that bounds, zonotope that's present in the cis inclusion that bounds this constraint zonotope. And the choice of approximation point gamma is such that it minimizes this expression, and it is derived in the paper why this choice gives a better result for the mean value extension. For the first order extension, we propose to choose approximation point as close as possible to the center of the zonotope. However, in the description of constraint zonotopes, there are cases in which the center, which is not the geometric center of the constraint zonotope, the center of the representation, it may not belong to the constraint zonotope itself. In this case, we compute an equivalent representation of the constraint zonotope in which the center is a desired point that is inside the set. Here we have a figure that compare different choices of approximation points. In the left side for the mean value theorem of mean value extension, on the right side for the first order Taylor extension. And in red here we have the choice that is proposed above, and is the best choice. And in blue we have on the right side have the choice that computes the equivalent representation inside the center, which is the best choice for the first order Taylor extension. So now I show an example, one of the examples of the paper that is state estimation of a quadratic water with V. The named equations are given like these equations on the left. The measurement is provided by GPS, a barometer, and IMU on this bounds on the measurement noise. These are the bounds considered for the disturbance and initial set, and the complexity of the constraint zonotopes are limited to 40 generators and 12 constraints. Here show figures, slide I show figures to illustrate the results that were obtained. We compare the figures on the top, compare the mean value extension using constraint zonotopes and using zonotopes. The constraint zonotopes is in red, zonotopes in green. And it's notable that the constraint zonotopes can give better results. These plots show only the interval rule because the complexity of the cells is very high to do conversion to half space representation to plot. Unfortunately, the toolbox that we supported, we need to provide the half space representation. So, and below we have a result comparison between zonotopes and constraint zonotopes for both mean value and the first order Taylor extensions. And it's notable that the radius, which is one of the measures that we use, one measure that we use for the size of the constraint zonotopes and zonotopes, the constraint zonotopes are able to provide smaller sets than zonotopes. However, if I are not learning failure extensions, a reasonable increase on computational complexity in the first order Taylor extension have more significant increase in computational time. Now I will move to systems of nonlinear measurement and invariants. So besides nonlinear dynamics, here we consider also nonlinear measurement, and we consider that the trajectories of the system satisfies an equality constraint for all the time instance. And this is common in the real plants. For instance, we have some example in mechanical systems that have autonomic or non constraints. And for instance, when we are doing a state estimation of spaces that are not Euclidean, in case which is state estimation, we have you want to estimate rotation matrices or quaternions, and these entities must satisfy some equality constraints. They satisfy equality constraints. And this the work presented in this part was published in another paper in Automatica, and also collaboration with Professor Joseph Scott, and Professor David Raymond. So the idea here is, instead of using a prediction update algorithm, we will use a three-step algorithm. The first step is the nonlinear prediction step, developed in the other part of the presentation. The update step now is nonlinear, so we cannot use a synchronous expression like in the linear case. And we consider an additional step, which we call consistency step. And this step basically try to tighten the set within the update step using the equality constraints that the system, the trajectory of the system satisfies. So the prediction step, as I said, basically based on the previous part. But here we allow the approximation point to belong to the interval rule of the sets instead of only the sets themselves, because this still provide valued enclosures, given the way that we derived the prediction enclosures, the other part. This is still valid. But since we allow to choose the points in a larger region, which is the interval rule, it can lead to positive more correct results. You have points that are outside the set, but inside the interval rule, that give less conservative enclosures. So for the update step, the first method is based in the mean value theorem. Basically, we can using the mean value theorem, we can write the update step, which is originally this expression, as we can prove that it's contained in the generalized intersection of two constrained zonotopes. And in the second, which y is given by this expression here, which is a constrained zonotope. Since we can compute now the update step as a generalized intersection, which is two constrained zonotope for the also nonlinear case, we have a big advantage if compared with the zonotope methods, which for the nonlinear case, they usually over-approximate this second set by strips that are very conservative because there is at least the method in the literature that the strips they are conservative because the way that they're computed, they have a lot of interval dependency, a lot of wrapping effect in them. And besides that, they are computed, the intersection with strips, they are computed in one strip per time, which one dimension of the measurement per time. So we have an iterative intersection which give more wrapping effect in the case of zonotopes. In this case, we just this expression, and there's not iterative procedure, and it leads to a more accurate result than zonotopes. In this case, you have to choose a real matrix to do this generalized intersection, and it's possible to show that if you choose this matrix as a midpoint of the interval matrix, this is I didn't put this slide, it's the Jacobian again of the nonlinear mapping G. if it's the midpoint of the Jacobian of this mapping, then you can lead to a more accurate enclosure. We also proposed a second method for update step, which is based on the first order Taylor expansion. It is also, in this case, also it's possible to write the problem as a generalized intersection between two constrained zonotopes. And again, this we have the enclosure is different, has more complexity. But again, we have the advantage that we use just a generalized intersection to solve the update step instead of doing iterative intersection with conservative strips. So for the consistent step, we have also the mean value method and the first order Taylor method. They are very similar to the case of the update step. It's basically we say it's analogous in the sense that this is can be referred as additional measurement in which we have a measurement 0 and this mapping again. And as in the case of the update step, you can write the consistency step as a general intersection between two constraints on top, which could be both computed efficiently. So now, one of first example that was in the second paper, which is a nonlinear system, which is a nonlinear dynamics nonlinear measurement. The considered bounds are given by these sets here. And in this case, we limit the complexity of the zonotopes to 8 generators and 2 constraints. In the top, we have the first three steps, the time 0 and the first 3 time steps, which shows that and here we're showing the results obtained in zonotopes without a consistency step because the methods with zonotopes are not. Sorry, in this case, we don't have. I'm confusing the two things. Okay, you have only the linear measurement. Then here, yeah, there's the methods that are proposed in Alamo and Combastel with nonlinear measurement, and comparing with the methods that are proposing constrained zonotopes. As can be noted, the sets produced by the constrained zonotopes, they do not explode with time. We are zonotopes, they increase to infinity. They keep increasing the size. As can be noted also in this figure that shows the radius, the zonotopes, they go to infinity, the size of the sets go to infinity, while the constrained zonotopes, they remain around a certain value. And in this case, since we have a nonlinear measurement, we have the computational times of the zonotopes increase a bit, and we have a comparison of computational times. It's very reasonable. There is a slight increase, but not very much as in the other case. Very big. So now I go to the second example, which besides nonlinear measurement, we have also invariants, which in the case is measured using quaternions. As I said in the other part of the talk, this quaternions is satisfy an inequality constraint. In this case, the norm is equal to 1 because they are the rotation quaternions. So these are the equations of the system, which are the nonlinearity and other part nonlinearity in the dynamics measurement and also in the equality constraints. And we assume these bounds in the simulation, and we consider, besides the consistency step, we consider an intersection with a set that we know that contains the region that is defined by the unitary norm, which is a unitary box of dimension 4. So in this case, the set complexity of the zonotopes are limited to 12 generators and 5 constraints. These are the results for the second example. We compare the zonotope methods with the constrained zonotope methods. In this case, plus F means that we're considering that feasible the intersection with that region that is the unitary box. Plus C is plus consistency step, plus FC, the feasible region, and the consistency step. So here we have that for the mean value extension, it's only possible to have enclosures that are not increased, only increase with time. if you consider the consistency step and use consistent zonotopes. In the second case, we have that the first order Taylor extension is capable of providing enclosures that do not explode without the consistent step. But with the consistent step, we are able to get enclosures that are arctic. Here we show the average radius ratio between the 10 results. We have the constraints isotope are able to provide the cells that are only 6.71%. In case of the size of the zonotopes, in case of mean value extension, in case of first order, only 5.12%. And I have just a light increase in the execution time, about 22%, 10%. Now we go to the last part, which is a very brief overview of the work and present the future work. So just a quick overview. In this talk, we discussed the method that we propose for state estimation of system nonlinear dynamics. The methods that considered for the first time a nonlinear prediction step using constrained zonotopes, and we proposed different methodologies, one based on mean value theorem, which is the mean value extension, and another based on first order Taylor expansion, which is called first order Taylor extension. Actually similar names to the interval methods, classical interval methods. And also addressed the problem state estimation of systems with nonlinear measurement invariants, which for the first time we proposed methods for the date step with nonlinear measurement using constrained zonotopes, and we also proposed a consistency step using constrained zonotopes to take into account for the invariants, and proposed two different methodologies. Again, one based on the mean value theorem and another based on the first order Taylor extension. And both all these methods were capable of providing more accurate bounds in comparison to classical zonotope methods that are in the literature. In the future work, we plan to think in ways on how to reduce the computational cost of the methods. And also we seek for alternatives for the mean value theorem and first order Taylor expansion to compute enclosures that are constrained zonotopes. So thank you for your attention.
Okay, many thanks for a very interesting presentation. And now I would like to hand over the microphone to the audience. Are there any questions already? So since I do not see any question at the moment, let me start with asking a few questions. Maybe we could start with the slide 17, because you have been very quick there when presenting the results. You have said something about the increase of the computational time, and did I get it correctly that this is a computational time per discretization step that you mentioned there?
Yeah, it's a very average computational time per time step of the simulation.
Okay, and then there's one information missing for me. Since you took into account, let's say, some kind of real-life example here with a quadrotor system, what is the discretization step size of your dynamic system model?
Okay, yeah, this is
just to judge a little bit how much, let's say, 100 milliseconds is.
Yeah. I mean, this is one of the reasons that we seek for ways to reduce the computational cost. In this case, it works because it's a simulation, but in your system, the sampling time is actually 10 milliseconds. So it's much smaller than this time. Okay. And including the zonotopes, that cannot be applied in the system in this time. So yeah, this is one of the reasons that we seek for ways to reduce the computational cost.
Mm-hmm. And this already, I think, gives rise to my second question that I would like to ask. Throughout the presentation, you always consider discrete time system models. Do you have any ideas how to generalize this also to continuous time dynamics? Because when you would be able to consider continuous time dynamics, maybe the integration from one time step to the other, where you have measurements, I think this could be simplified.
At least in my cases, we did not, we only addressed discrete time systems. But yeah, we did not have thought in a way yet to extend. Maybe based on some other literature, there's some out of Matthias out of work of continuous time systems. Maybe there is a way to say the English word is missing, but it's like not to use the methods, but maybe to give ideas on how to extend this.
Okay.
To the continuous time. We had not worked it yet.
Yes, because I think it would be possible, for example, to generalize those Taylor series or temporal Taylor series based approaches that are, for example, included in the approaches of Rudolf Lohner or also of Nednedialkov in V-Node LP. I think those could be generalized also to the constraint zonotope setting. But now I see that we have a question at the moment, just a comment at the moment from Armando. Davide, please go ahead. Just give your comment.
Hi, Andreas. Yeah, I just wanted to mention that indeed this is just a MATLAB implementation. So I think that if we implement this in C, for example, maybe the computation time could be compatible with the sampling time.
Okay. So great.
Hi, David. I didn't notice that you are.
So now I see that we have a question from Bernd.
Yeah, Andreas, thank you very much. This is exactly the right slide to see, because I wonder if you can include the discretization error of your discretization into your noise. Did you do that, or did you completely ignore the discretization error?
For the moment, we are ignoring that.
Okay, but it could be included, I think, in the W noise.
Yes, of course. When
you made an estimate for that, you can include it, and then because otherwise there are people around in the world which will doubt your results because they tell you your model is continuous, and you make a very, very exact and very nice estimate for the discrete time approximation, but without discretization errors, some people would criticize you for that.
Yeah, I agree. If it is applied to a continuous time system, it is not exact anymore for the discretization error. The only maybe a challenge is to compute a bound for the discretization.
Yeah, that can be done with the methods Andreas already mentioned, like in Lohner's method, for example. There's you can rewrite Lohner's method in some sense as a discretization, and then you can bound the error. That should be possible with relatively small efforts.
Yes, and in the simplest case, you just obtain an interval box that is representing the time discretization error, and an interval box is a very extremely simplified zonotope in this meaning, and this is something you can directly include.
Okay, so thank you very much.
Okay, do we have other questions in the audience? Yes, in fact, I have a further question on the slide 19, where you started with yes, the extended system model where you have additional invariants. And that's really something I like very much, because in many real-life systems, for example, you have some kind of physical conservation properties, something like a conservation of energy, conservation of momentum, mass, volume, or whatever. And I think if such invariants then just express those conservation properties, they can easily be used as some kind of virtual measurements in order to reduce also overestimation that just results from interval-based wrapping effect, dependency problems, and things like that. And that's really something, just as a comment for practical application, that's really something that is very interesting. Yes, and besides this comment, I also have a question, because what you assumed at the moment is this explicit dynamics that from the time step k-1 till the time step k, you really have this explicit representation of a discrete time state space model. Did you already think about generalizing this approach also to descriptor systems?
Yeah, we have a work that was published in the IFAC 2020, which we addressed the case of linear discrete systems. So
okay.
We started that is not went to nonlinear. Yeah, but the linear case using constrained zonotopes, comparative zonotopes as well. We have developed the method for state estimation for the linear case.
It was which IFAC conference? It was the World Congress in 2020?
Yeah.
Okay.
That's our first virtual conference that they.
Okay, then I'll have a look at the proceedings volume. Okay, further questions from the audience? This doesn't seem to be the case. Then again, many thanks, Brenner, for your very interesting presentation, also for answering all the questions. And yeah, from my point of view, that's all for today. And I just wish you a nice, for you in Brazil, still complete Friday, more or less, since yes, for you, it's already early in the morning. And for the rest of the audience here, have a nice Friday afternoon, evening, and weekend. And we'll see each other again in Friday in 2 weeks. And yes, I'm looking forward to the next meeting. See you soon. Bye.
Thank you.